Okay, guys, are you ready? Yes? Okay, so this is our first unit. It's unit 5. And we're going to talk about how to locate objects in the sky. And again, as I mentioned before, this is part of the astronomy part of it, okay? So we use specific numbers to locate objects everywhere, anywhere in the sky. So this is similar to what I was saying earlier about our address. So if you would want to have something delivered, you need specific coordinates, okay? You need an address. Have you guys heard of geo data or geolocations? No? Yes? You go to Google, for example, you can find where you are. Let me go back to that software, the one that I was using. Hopefully I didn't close it. I think I did close it. Let me check in here quickly. Because if I did, it's still open, good. Okay. If I go to the location, it says San Bernardino, North America. You see here these two numbers? Can you read what it says in here? Latitude and longitude. Those are the specific coordinates of where we are right now, okay, in San Bernardino. We are 34 degrees north of the equator. So if you go to the equator, that's 0 degrees. And you move from the equator all the way to the North Pole, you would have done 90 degrees, okay? If you go from the equator and you go down all the way to the South Pole, how much did you do? Negative 90 degrees. You went in the opposite direction, okay? So you could write in that case south. So if you go to Sao Paulo, for example, or I don't know, somewhere in the southern hemisphere, the numbers will not have an N next to them, will have an S next to them, okay? So this is called the latitude of how far we are from the equator. We are at 34 degrees, 12 arc minutes, okay? There are 60 arc minutes in 1 degree. Just like the clock, 60 minutes makes an hour, correct? And then 59.75 degrees arc seconds. So we're not just talking about a degree, we're talking about a fraction of a degree. You guys see that? Because 60 arc seconds will make 1 arc minute. So we're almost 13 degrees, okay? You guys see it? And if I divide the clock, so we went from 0 degrees, this is the equator, and we went all the way to 34 degrees, okay? What's the number that comes after 34 in terms of degrees? The number after 34, what comes? 35, very good, okay? Sometimes my 3 and 5, okay? So between this and that, there are 60 arc minutes, okay? To go from 1 degree to the next degree. But we are at 12 degrees, so 30 degrees somewhere in between, okay? Half of that is 15 degrees somewhere in here. So this is 15 degrees. But we are not 15 degrees yet, we are 12 degrees and almost 13 degrees. Do you see the number? 59 is almost 60. Do you guys see it? So it's almost 13 degrees. However, for all practical purposes, it's actually here. That's where we are, okay? But that's not only San Bernardino. A lot of places are on the same line, okay? So if I drive east or if I drive west in the same line, they will all have the same number. You see it? So this is the latitude. In order to zero in on San Bernardino, we need the longitude. And the longitude is this line, okay? That come like this, okay? And which side are we? Can you tell me what the number is for San Bernardino? You see the longitude? What does it say? 117 degrees. What's the first letter? Do you guys see it? West. West of what? You guys know? I'm sorry? The parameter? We're west of something. If we're in China, do you think we will have a W or we'll have an E next to it? Sorry? We'll be east of something. You guys see that? So there is a line that is 0. There is a line that is 0, and we're west of that line. Do you guys know what that line is called? Sorry? The equator is in the bottom. The equator is in the bottom. 0 is the equator. You go above it is north. You go below it is south. Correct? So this is 0. You go up, it's north. You go below, it's south. We're talking about this line now. There is a line somewhere which is 0 degree. You go this way, you're labeled W. You go this way, you're labeled E for east. W is for west. Does anybody know the name for that line? It goes through a famous city in England, and it bears that name, or that city. It starts with the letter G. GR. Have you guys heard of Greenwich? Okay. It's called the prime meridian. People agreed by convention that this is the 0 degree longitude. If you are on the east of that side, if you are in Italy, for example, or if you are in Egypt, or if you are in Turkey, or in China, they'll give you the E number. Okay? And if you are on this side, they give you the W number. You're west of the prime meridian, or Greenwich. Okay? So that's the convention. Is the earth flat or round? Do you guys know? Sorry. What? Don't tell me that, okay? We're back to this nonsense stuff, okay? Oh, okay, good. Okay. I thought for a second you're going to take me into that. Okay, good. I thought you're going to be called, and maybe we'll call help for you. 911, we have somebody who's... Okay. It's very close from a sphere, by the way, okay? So this prime meridian, do you guys see it? It extends to the other side on the sphere. Okay. I don't have the key to this. Next time I'll get the key so that we will see, because there is actually nice spheres in there. Okay. So imagine you have a sphere, like this is the Earth, okay? This is the Earth, okay? And there is this line. So on this side, I'm calling it the prime meridian, okay? This line, this longitude. Anything on this side is W, anything on the other side is E, for east. If I extend this line on the opposite side, it's called the dateline line. So basically the dateline. That's what distinguished yesterday from today. If you're on one side, you're in tomorrow. If you are on the other side, you're in today. Okay? So that's basically how yes?
Is the dateline straight or
Jaggedy, depending on the whole longitudes are kind of jaggedy a little bit because of the politics. Okay, some countries they want to be on the same time zone. Okay, than others. They don't want to be in different time zones. Okay, so we're at 117 degrees. We're past 90 degrees. Do you guys see that? So quarter of the way is 90 degrees. Halfway is 180 degrees. We are in the second quadrant. Okay? We're past 90 degrees. We're not yet at a full 180 degrees. We're not at the dateline. We're not in closer from Hawaii. We're this way. You guys see it? So this is the longitude. Again, it's in degrees and arc minutes and arc seconds. Okay? And there are 60 arc seconds in 1 arc minute and 60 arc minutes in 1 degree. Okay? So that's how we locate things on Earth. So if you go to Google and you have an address, it can give you specifically where that object is on Earth. Okay, so you use that extensively. So try to remember this concept because it's a useful concept that we're going to need for our stuff. Okay, let me minimize this. And let's go back into show. Okay. So these are the objectives of this unit. Okay. We're going to be learning describe the celestial sphere. On the way out, on the cabinets, you can look and you'll find something labeled celestial sphere. That's what we're talking about. Once I get a key to it, hopefully you guys can see it, okay? It's just a representation of the sky. Okay, so that's basically what we're going to be learning. And also, list of reference astronomers used in describing locations in the sky, list points of reference. Explain the, what is it typing? I don't know why it's doing that. Anyway, so is there something to stop this nonsense? It's kind of annoying. Okay, I think that's the one. Okay, good. I don't need that. Okay. Anyway, so explain the daily motion of the sky. Okay, and estimate the position of objects on the celestial sphere. So we're going to be learning that. Okay. So one concept that we're going to be looking at is the celestial sphere. So if you go out tonight, the sky looks like this dome. It's like a big dome. Okay. And if you look at the horizon, anywhere on the horizon, that is actually your zenith. I'm sorry, your zenith, your horizon. Okay, I'm sorry, I made a mistake here. The zenith is above your head. Okay, so again, so that is your horizon, and I'm not sure. I don't have my phone, I think, with me right now. So this is the direction of the east, and I am looking north. Therefore, this is the direction of west, and this is behind me is south, okay? So I am east, north, west, south, okay? That is my horizon. When I'm looking north, when I'm looking due north, and I'm extending my hand, okay, my arm is, I got hurt in soccer the other day, and my arm, I can't lift it up correctly, okay? If I'm looking due north, okay, and extend my hands, the right hand is going to be always east, correct? And the left hand is going to be west. Behind me is going to be south. The line that extends from my due north, that line, and then goes above my head, okay, and go due south. So there is a unique line in here from where I'm standing. This line is different than this line. If I'm looking from due north, above my head, to due south, this is called my local meridian. Okay? It's an imaginary line that passes from, this point is called zenith. Again, it's coming from Arabic, which means that it's the tip of the thing, okay? From due north to my zenith to south, that is my local meridian. Mine. Yours may be different, okay? because you're a little bit to the east, and hers is different than both of us because she is a little bit to the west of us. You guys see that? So this is unique to every person, to every place. But there is one meridian that everybody agreed on it, that's the prime meridian. That's the one that, okay, passes through Greenwich. That is the convention where everything goes through. You guys see that? So this is how we locate things, at least in terms of this celestial sphere. Obviously, we can't see the entire sphere. We only see half of it. The other half is hidden from us by the Earth. Okay? If the Earth somehow becomes transparent, then we can see the entire sphere. You guys see that? But at this point, we can't. The Earth is opaque. We can't do anything about that. Okay? And that's another thing. Stars in the universe, they appear to be sitting on the same point in space. Okay? For example, if we turn on this projector, they appear to be dots on this specific dome. And as a matter of fact, they are, but they are not. Some of them are closer than others. There is an element of depth that we can't see immediately. You guys see that? That we don't see. We see them all projected on the same dome, the same place, okay? But some of them are brighter than others, so there is an element of depth. So that you know, let me go back to the planetarium. Those three stars, النيلام, المنطقة, النطاق, from let me close this. Let me go back into Orion. Here. And now we need to zoom back because this is way too much. Okay, these three stars. These are Orion's belt, okay? If I click on a star, it will tell me a lot of information about it, okay? I don't know if you can read this. First of all, this star is called Al-Nitaq. It's a Ka, it's not a Ka, so that you know. It's a double star. Its magnitude, which means how bright it is, what I'm looking for is how far it is from the Earth, okay? And the distance, do you guys see it? 817 light years from Earth. Super, super far, okay? For example, Betelgeuse is closer. Betelgeuse, the distance is 497 light years. So they look like they're sitting on the same dome. But this one in Nitaq is far, far, far. It's almost twice as far than this one. You guys see it? So there is an element of depth that we can see. For us, we see them. For example, this is Al-Nilam, which is sitting on the same belt. The distance, where is the distance? The distance is 1,976 light years. More than twice as far as than this one. Yet in terms of light, both of them appear to be the same color, the same intensity. You guys see that? So that means that this one is far, far bigger than the first one. Okay? That means this star is far bigger. By the way, this is the Orion Nebula. Okay? So if you zoom in, it's on this side. Okay? And this is the Horseshoe Nebula. Okay? So again, this is the star we're talking about in here. This is Al-Nilam, which is 1,000, almost 2,000 light years away from us. So there is an element of depth that we don't see on the dome. We just see the star, dots in the sky. Okay? And let's look at the third one, just to complete the whole picture. Mintaha. This is almost as far than this one, slightly further. So this one is 800 light years, and this one is 900 light years. You're talking 100 light years. That's not close. Okay? That's not close at all. But there is an element of depth that we don't have. You guys understand? When we see things, when we go out and put our mat underneath and then we lay down and start looking at the sky, we see everything is happening on one, but there is a projection, an element of projection that we don't have. Okay? Okay, so let's go back and finish this thing in here. Okay, minimize this. And then the other thing also, the sphere appears to move. It's not sitting still. Okay? It's not sitting still. If you wait for 1 hour, everything moves from one location to the other. Okay? If you wait for 2 hours, everything moves in the sky. Why do you think they are moving? Sorry? Yeah, because the Earth is spinning. It's us that are moving, not them. They're too far away for us to notice their motion. The Earth, do you know how long it takes for the Earth? Oh man, we went back to that nonsense. Okay. Okay, good. Okay. So, do you know how long it takes for the Earth to go once around its axis? How long do we go once around our axis? 24 hours. So a lot of these questions, they are kind of obvious. Hopefully you guys picked up on that. So the Earth does 24 hours to complete one cycle, 1 day. Come tomorrow at 7:21, we would have completed the full cycle. You guys see that? Everything that is the sky now will be back in there, except those planets and that we were talking about. Okay? They may change position slightly, but everything else will be in the same location. Okay? So the point being in here is 24 hours. So in 24 hours, we do full circle. We start from here, 24 hours later, we're back in here. How many degrees is full circle? Do you guys know? 360 degrees. So in 24 hours, we do 360 degrees. How many degrees we do in 1 hour? Remember, in 24, we do 360. So in 12 hours, how many degrees do we do? 180, correct? Half of 360. And in 6 hours, what? 90, half of 180. And in 3 hours, 45 degrees, correct? Half of 90. And in 1 hour? Sorry? What? Yeah, say it. 15 degrees, yes. So in 1 hour, we do 15 degrees. Why? Because 15 and 15 and 15, 24 times actually, if I multiply this by 24, I get 360. Okay? So if you go tonight, time it. Okay? Time it, do time, okay? Look at the clock and watch a star. Pick a star, it doesn't matter which one, star. Okay? Even a planet for that matter, star. Okay? Planets, they're far enough for this to be noticed too. Okay? But a star is better. Pick a star, it doesn't matter which. Okay? And note its position versus a tree, for example. Okay? Or versus a mountain, or versus a building of specific, or versus a window or something. Okay? So that you know, if I go from here to here, how many degrees? From here to here, how many degrees? 90 degrees. Half of that is what? Yeah, so if I go from here to here is 90, but if I go midway, it's 45 degrees, correct? And if I go third of that, so imagine you divide this into 3. So this is 1 and 2. So this is about 15 degrees, correct? So if the object was here, I'm looking at, in an hour, it would have moved about 15 degrees. Okay? You don't need sophisticated devices like a sextant or something to measure the angle. You can just go by your hand. Okay? You don't need a lot of equipment to really do this. You guys see that? And if you get another hour, it's another 15, 15, 15, 15, 15, 15, and so on and so forth, okay? You guys see that until the whole thing completes. So everything moves, and the reason why it moves, it's not because they move, it's us that move, okay? We are the ones that are in motion. Similar to an experience that some of you probably did not experience, but if you sit in a train, and then all of a sudden, you feel like the train is moving until the other one passes by. Actually, it's the other train that was moving, okay? You guys understand? Did anybody experience this thing? Okay. Yeah, some of you probably did. You really have to have traveled a lot in trains to notice this. You're sitting in your train, and there is too much engine going on for you to think that maybe it's your train that is moving, but it's actually the other train that was moving all along. And you don't see that until that train passes by and you see the trees or the building next door are still in their place, okay? Then you realize it's not your train that was moving, it's the others, okay? So that is exactly this impression too. We think that these objects move, but they are not moving. It's us that are moving, okay? It's the other way around. It's relative motion. Because the Earth is spinning around its own axis. Okay, this is part of the culture now, okay? This depends on the culture. I already mentioned the Subaru, for example, or the Pleiades, or the Six Sisters, or the chandelier, and every culture divides these things, they look at these things, and they start seeing things in them. Honestly, I looked so many times at this constellation, and I've never seen a lion. I tried, okay? And sometimes I try to convince myself, hey, there is a lion, I see its tail and things like that. But then afterwards, no, I don't see it. So it depends on the culture, depends. But these are fixed shapes in the sky that people associate with objects like this, and they start to build all kinds of mythology associated with it. I mean, my mother used to tell us all kinds of stories about the thieves and how they stole the hay and the sheep, and that the hay left a mark on the ground that it printed itself in the sky, and that's what the Milky Way was, okay? Other stories in the Greek mythology also talk about milk being dripped, and there's also so there are all kinds of stories in there. Orion, for example, I was talking about earlier about it, and how he's hunting for the Taurus. In other mythology, actually, he's not hunting for the Taurus. He's actually being punished by Zeus, and he's actually chasing the six sisters or the seven sisters, trying to have his way with them, okay? He's punished that he will never catch them, okay? Every night he goes behind them, and they always lead him away. So there are all kinds of stories in here. They're just folklore stories, okay? So they're not science, okay? So don't believe any of those things, okay? Don't put too much weight in them. So again, this is part of the, there is a different things. There are two things, okay, that you need to understand. There is constellations. Those are named constellations. There are 88 of them. You're not required to memorize them. But it's a good idea to know some of them, okay? So at least you navigate your way through the sky. And then there is another thing called the asterism. Asterism is any shape in the sky that you can identify. One of the famous asterisms are the three stars that I'm going to mention right now, called the winter asterism, and they are these three stars. If we go back into planetarium, and let's zoom out. Okay, these three stars. These are called the winter asterism. This is Canis Major, and this is part of Canis Minor, and this is part of Orion. These three stars, Ceres, Procyon, and Betelgeuse. Okay, for those taking my Astronomy 125, the lab, you need to remember this star and this one. And this one also, they are part of our activity at some point. We're going to do all kinds of studies on them, but not in this context. They're called the winter asterism, because you see it's like an equilateral triangle. Do you see that? You see them? So they're actually a famous asterism because they're not part of the same constellation. This constellation, this is different constellation, this is different constellation. But the three of them, they form a good triangle that you can find yourself through it. So if you're lost in the desert at night, you can start to locate the east from the west if you recognize the shape in here, especially in winter, okay? Because this is a winter effect, at least here in the northern hemisphere, okay? They're called the winter asterism, or the winter, the winter triangle, or I don't know. So there are three stars. They form a perfect equilateral, not perfect, but close from a perfect triangle, the three of them, okay? Again, myself, I always use these three stars, can I get into a place where I don't have a, when you think that you are on nowhere, all of a sudden you discover that you are somewhere. You have a planet in there, okay? Or a star. I'm sorry? Yeah, because of the seasons. We're going to talk about the seasons, yes. The constellations change because of how the Earth rotates around the sun. That's a good question, okay? There are different three types of constellations so that you know. Those that are sitting on the ecliptic, and those are seasonal constellations, from season to season to season to season, okay? And please read the book, okay? Don't rely on this presentation or the PowerPoint. You have to read the book, okay? So there are seasonal constellations, and there are the circumpolar constellations, the constellations that are there almost on the entirety because they go around the Polaris, okay? One of them that is a famous constellation is Cassiopeia. The Cassiopeia is actually depending on the time of the day, the night, I'm sorry, it can be a 3, or it can be a backward 3, or it can be a W, or it can be an M, depending on its location, because it goes around Polaris, okay? As a matter of fact, let me do this. Let me find Polaris and show you that, since you asked that question. And then there are some constellations that are neither. They're basically irregular constellations. So there are seasonal constellations, the ones that from season to season to season. There are circumpolar, the ones that go around the Polaris, and they stay almost every night. And then there are constellations that don't belong to neither, okay? Irregular constellations. So let me go back into finding Polaris. No, not the time. Yeah, I need the time at some point. No, not this one. Let me go into, no, not the location, I'm sorry. The search. Polaris. Here is the northern star, okay? I'm going to zoom out a little. And let me turn on the constellations so that we see them. What are the constellations? No. Now here are the constellations. So this is an asterism, and these are the constellations, not the boundaries. We want just the constellation label. No, we want the constellation lines. Okay. So this is Polaris, and it's the extension of what looks like a pot in here. Okay, so that's one way of finding it. Look at this one. It's going to go around it. Okay, and where is here is, you see what looks like a W in here? This is Cassiopeia. Okay, I want you to pay attention to it and see how it goes around Polaris. Okay, and let me put the horizon on. So this is as if I'm looking at the sky, okay, from the Earth, okay? So right now it's a W just above the horizon. And I'm going to take the time, and I'm going to unfreeze it. And I'm going to make it move faster than this. Okay, slower. So this is too much. It's going to be dizzying. You see, some constellations, they stay around Polaris. Those are called circumpolar constellations. What is Cassiopeia? It's an M now. Okay. So if you go to, you will see from time to time some objects that are flying. Those are actually satellites. Okay. Right now it's a backward 3. So if you go to the desert at night, And if you can stay awake the entire night, you will notice this pattern. Okay. And now it's going to go back into a W sitting just above the horizon. You guys see the difference in the constellations? Some of them, they stay there because they're very close from the northern star. This one doesn't move. Polaris does not move. And that's why it's a good idea to find it, to at least navigate that points toward the north. Okay? Make sense? So let me go back and to stop this. This software is free, by the way. You can download it, and you can do all kinds of things. By the way, for those sitting in Astronomy 125, we will be using it a lot for some of our labs. Okay. So again, this is a famous constellation, Leo. Okay. And this is actually an example of seasonal constellations. Okay. And this is another constellation, Cygnus. Okay. It's a good idea to remember some of them. Okay. Oh man, we went back to this thing. Okay. It's a good idea to remember some of these constellations, the Big Dipper, the Teapot, and some of these famous constellations. Okay. Anyway, this is how the Earth is actually. The Earth is a little bit tilted on its axis. Okay. The Earth is tilted. So what do I mean by that? Let me erase these things in here and explain this point. If I have the sun in here, so this is the sun. And if I have Mercury in here, and if I have Venus in here, and this is the Earth. All of this, they're moving almost on the same plane. Okay? They're moving on the same plane. Not to above, not to below. They are on the same plane. If you find something that is off, that means that thing went into a collision of some sort. Imagine yourself making a pizza. Okay? You got the dough. What do you do to it to flatten the pizza? Roll it. That's it? I'm sorry? Yeah, you can spin it fast enough, it's going to flatten. Okay? You spin it fast enough, it's going to flatten. That is because of something in physics called the angular momentum. Okay? The angular momentum forces these things to be in the same place. So if you go and look at an object and you find it not on that plane, that object must have been hit by something or was captured or something else, so it happened to it. You guys understand? But from the original makeup, whatever made the solar system, they all exist in the same plane. This plane is called the ecliptic plane. And if you go and look at the sun, where it moves mainly on the ecliptic. It moves on the ecliptic. The moon is more or less on the ecliptic. Venus is more or less on the ecliptic. Because we are moving on the ecliptic and we see everything on that plane, okay? You guys see that? That's why everything appears to be on the ecliptic, okay? Well, the Earth, if I'm going to draw the Earth a little bigger, this is how it looks like. It's spinning not in this direction, but in this direction, this way, making an angle of 23.5 degrees, its axis of rotation versus the ecliptic. Do you guys see that? So it's tilted with respect to ecliptic. While it's going around the sun, it's spinning not its axis of rotation and motion in the same plane. They are not. There is a 23.5 degrees. And this points to the star Polaris. That's why Polaris earlier in that animation did not move on a 24-hour basis. Everything else was moving because the Earth was spinning. The thing that was here started to go around it. You guys see that? Polaris did not move because it's actually the axis of rotation points toward Polaris. Okay? That's really why Polaris, they don't appear to be moving. Everything else appears to be moving around Polaris because Polaris happened to be in that direction. Okay? What are we doing on time? Okay. We still have, we may finish a little early today. Okay? Okay? So that's the point I'm trying to make in here. So the zenith, again, is coming from the Arabic word, which is the tip, and the nadir, the nadir, it's coming from the Arabic word also nadir, the opposite. That's what it really means, or the symmetrical. Okay? So the opposite to zenith is a nadir. Okay? So the tip, opposite to it, is the nadir. Actually, the word is nadir. Okay? But sometimes when you go from one language to another language to a third language, by the time it arrives to you, it has been changed so much. Okay? And then you have the north and the south. So the northern hemisphere and the opposite to it, that's the southern hemisphere. For me, it's a different perspective. For you, it's a different perspective. Your zenith is immediately above your head, okay? That's your zenith. Like, for example, that would be the zenith for this building. Do you guys see where all of the points meet? Opposite to it, if you extend this and make it into a sphere, is the nadir. That's what translates really to the opposite, okay? And then, of course, you have east, west, north, and south, okay? So that's how things are. So depending on where you are, you have a horizon, you have east, west, north, south, and then you have your zenith, which is making usually an angle. Unless you are in the North Pole, then your zenith is going to be the North Pole, the Polaris. Make sense? Again, I was talking earlier about the longitude and the latitude. This is a city in the eastern hemisphere, in the eastern coast, and that's its latitude and its longitude. Those numbers define uniquely a point on Earth. Make sense? So the longitude is from the prime meridian that you can clearly see passes through England, good chunk of France, Spain, Algeria, and then parts of Africa, I think Nigeria, and then goes through the ocean and comes back from the other side. Okay? So that's the prime meridian. Then anything on this side is west. Do you guys see the other side? It has an E next to it. That's the east. Yes? So, and for that city, it happened to be almost, what, 70 degrees or 69 or something like that? And we are at 117 degrees. Okay? Also, 0 degrees is the equator. Anything above the equator is going to be north and goes all the way to 90 degrees. And anything below is south and goes all the way to negative 90 degrees. Okay? Or 90 degrees south. So that's how the Earth is divided. That's how things are determined on the surface of the Earth. Okay? Now, if you take this Earth and you project it in the sky, so what was the equator on Earth becomes a celestial equator. You guys see it? And what was your prime meridian becomes your origin for measuring locations in the sky. Now we have the ability, so this is the Earth in here. We take the Earth and we blow it up to cover the entire sky. This is called the celestial sphere. And objects on the celestial sphere are determined in a similar fashion, except instead of calling it latitude and longitude, we have the right ascension and the declination. So the declinations are above the celestial equator and below the celestial equator. And they are in degrees. Okay? But what was before, the longitude, now called the right ascension, RA. Okay? So the right ascension, instead of degrees, it shows hours. So full circle, how many hours? I'm sorry? 24 hours. Okay? So now objects in the sky are located, they're similar. You can convert from one to the other. Okay? Remember, every 15 degrees is 1 hour. Okay? So that's basically the number that you're going with. Okay? So we have the right ascension and we have the declination. That is to locate objects in the sky on the celestial sphere. Okay? The advantage of having it to have it right ascension in an hour is actually very good, because the Earth is spinning on its axis and you're moving with the Earth. So if I tell you this star, for example, has a right ascension of 13 hours, okay? And right now, it's on my zenith, okay? And let's say, for example, now it's 10 p.m. Where would it be in 3 hours? So right now, 13 hours plus 3 hours is going to be 16 hours, okay? So that's basically how it is. It's very easy to work with these numbers, okay? There are two conventions for the right ascension. There is the J2000 standard, and there is the different standard that is going to be. Okay. We have another unit, Unit 6, and it's almost 8 p.m., okay? You guys have any questions for me first or not? Do you understand what this class is? Yes? Okay, I'm going to stop it at this unit, Unit 5. But I'm counting on you guys when you go home to read the rest of the units, okay? Unit 6, okay? And try to understand, try to go through all of it. There is far more details. So what we do in class is not everything, so that you know, okay? What we do in class in here is for me to present to you the lecture and incite your answers and incite your participation, and hopefully we understand things. And then you guys are going to go home and do the reading from the book, okay? This week we have units 5 and 6. So next week when we meet, we have more units in addition to unit 6, okay? So we're going to be building on it, and we're going to discuss some of these things later on. Make sense? No, you don't need, I mean, I hope that you can read 1 through 4 on your own, but you're not going to be tested on them, okay? 1 through 4, by the way, is an introduction to what I was talking about earlier, okay? So in terms of the things like that, and where we are located and things like this, okay? Questions? No? Well, have a good rest of the night, and I will see you next. Yes, hold on. Everybody have a question? Please do understand what you're reading, okay? Yes, okay? Again, there is a YouTube channel. It's DJ Bouzidi. If you want to follow a lot of these things that I do in here, it's the same thing in that.
We're Tuesdays and Thursdays, right?
Tuesdays for the lab. Are you meeting? Are you in the lab?
120.
120 is only Tuesday. I mean, only Wednesday. Thursday, I'm sorry.
Thursday.
Yeah, are you in the lab or not? You're not enrolled in the lab, then you're off the hook. Your Astronomy 120?
Yeah.
Astronomy 120 meets only today.
Okay.
Okay?
So
Those who are sitting in my Astronomy 125, like those souls, yes, they are. They're in the come on Tuesday. Okay? Have a question? Hold on, let me close the thing in there so that they don't.